Hi, my name is Liat and I will present our paper Constant RMR Group Mutual Exclusion for Arbitrarily Many Processes and Sessions, which is a joint work with Gary Taubenfeld. First, let's look at this example. Assume we have two processes, green and blue, and the square in the middle is the shared memory they both want to access. When the green process wants to access this memory, it locks the memory so other processes, such as the blue process, may not access this memory and must wait to their turns. When the green process finishes with this memory, it releases the lock and then the blue process may access this memory. But what if I tell you this square is a classroom and the green circle is a computer science professor while the blue circle is an economic professor? They both need this classroom to teach a class for students in their faculty, but they can't do this together in the same class, right? So they want to enter the classroom separately, but I told you they want to teach students, so they can't lock the classroom for all the other people. They want to lock the classroom only for people from a different faculty. Now let's look at this scenario. All the green circles are the computer science professor and his students, while the blue circles are the economic professor and his students. When a computer science student or the professor enters the classroom, he locks the room so only the computer science professor and his students may enter the room concurrently, while the economic professor and his students must wait. And only when the computer science professor and all of his students leave the room, the lock is being released and the economic class may begin. The group mutual exclusion problem was first introduced by Jan in 1998. In this problem, n processes request m sessions. Session is like the color from the previous slide, and they want to enter their critical section. Processes that request the same session can enter the critical sections concurrently, while processes that request different sessions must wait. This problem is a generalization of the classic mutual exclusion problem, which is the problem we talked about in the first example, and also the readers and writers problem, in which readers may enter their critical sections concurrently, but writers must be alone in their critical section. To solve mutual exclusion problem using a group mutual exclusion algorithm, we can define that each process uses its own identifier as its own session. And to solve the readers-writers problem, each writer uses its unique identifier as its own session. And we have another session which all the readers attend to. We have 4 sections for a process to be in. The remainder code, where a process may execute its code without accessing any shared memory. The critical section, where a process may access the shared memory. The entry code, where a process checks if it's enabled and can enter the critical section or must wait to its turn. The exit code, that a process executes after it completes its critical section, and by doing so, it may release memory locations or let other processes know they can enter the critical sections. So the problem is to write the code for the entry code and the exit code such that the following properties are satisfied. Mutual exclusion and starvation freedom. These two are generalized properties for the same name properties in the mutual exclusion problem. And also group concurrent entering and group bounded exit, which are first introduced in our paper, and I'll explain why later in this presentation. Mutual exclusion property is to ensure that if two processes are in their critical sections at the same time, then they request the same session. In the classroom example, it means that if two students are in the class together, then both are from the same faculty. Starvation freedom property guarantees that if a process wants to enter its critical section, then it eventually enters its critical section. Group concurrent entering property is first introduced in our work. It's a lot of words, but in short, it guarantees that if all the processes that are active, meaning in the entry code, critical section, and the exit code, request the same session, then always at least one process enters immediately to the critical section. Group bounded exit is also first introduced in our work. In short, group bounded exit guarantees that if there is a process in the exit code, then always at least one process completes the exit code immediately. We also have fairness properties that define the order processes and sessions may enter their critical sections. If two processes request different sessions, then the first come first served property guarantees that the process that came first will enter the critical section first. We also have first in, first enable property, which define the order of processes from the same session, as opposite to the first come first served property, which define the order for processes that request different sessions. The first in, first enable property ensures that if a process enters its critical section, then the process that has started the algorithm before him and requested the same session will enter the critical section too. Remote memory reference. In a computer, depends on the memory model, data can be stored in a remote memory or in a local memory. Access to local memory is local reference and is much faster than accessing data that is stored in remote memory that required a remote reference to access this memory. Remote reference generates traffic on the network between the process and the memory, may affect other processes and makes them slower. We want to reduce the number of remote references as much as possible. We have several memory models. The first is the simple shared memory. There is only one memory and any access to this memory is remote for all the processes. The second is the current caching, CC in short. In this model, each process has its own cache and accessing a memory location from this cache is considered as local, while accessing the shared memory is considered as remote. The third is distributed shared memory, DSM in short. In this model, there is no single shared memory. All the processes have locally a piece of all the shared memory. Accessing a memory location in your own piece is considered as local, while accessing other processes' pieces is considered as remote. The important complexity in the group mutual exclusion problem is RMR complexity, which is the maximum possible number of remote memory references during a single execution of the entry and the exit code. The group concurrent entering property is first introduced in our work and is stronger than an existing property called concurrent occupancy and is slightly weaker than another property called concurrent entering. I'm not going to explain these two properties because we don't have the time for it, but you can read about it in our paper. Another property that is first introduced in our work is group bounded exit, which is stronger than terminating exit and weaker than bounded exit. Again, we don't have time to explain these properties and the differences between them, but you can read about it in our paper. So why did we need to create weaker properties? Why can't we satisfy the existing stronger properties? In 2004, Danek and Zilakos proved that there is a lower bound for RMR complexity in DSM model. They proved that any group mutual exclusion algorithm that satisfies mutual exclusion, starvation freedom, concurrent entry, and bounded exit can't achieve a lower RMR complexity in DSM model than omega n, where n is the number of processes. We wanted to create an algorithm with a constant RMR complexity in DSM model, so we needed to make changes in the properties we satisfy. Our goal is to create a group mutual exclusion algorithm that works with arbitrarily many processes and sessions, so the algorithm doesn't know in advance the number of processes and the number of sessions. Also, we wanted to create an algorithm with a constant RMR complexity in both the CC and the DSM models. Our algorithm is the first to satisfy each of these properties. There is a group mutual exclusion algorithm with a constant RMR complexity in CC, but it's missing a lot of important properties such as concurrency property. Atomic instruction set. Our algorithm uses this 3 atomic instruction set that is supported in most of the modern processors. Atomic read-write, fetch and set, which returns the current values and replace it with a new value atomically. Compare and swap, which replaces the value only if the current value equal to another value. It performs the check and the replacement atomically and also returns true if the values are equal. The algorithm. Algorithm satisfies all of these properties: mutual exclusion, starvation freedom, group concurrent entering, and even strong group concurrent entering, which I'm not going to explain in this presentation, but you may read about it in our paper. Group bounded exit, first come, first serve, first in, first enable. The numbers of processes and sessions are not priorly known. Constant RMR complexity in both the CC and the DSM models. Constant space per process and ON in total. And instruction set that is supported by most of the modern processors. And also, algorithm is the first to satisfy these two marked properties. The algorithm maintains a queue of nodes using a linked list with head and tail, and is inspired by the MCS queue-based algorithm for mutual exclusion problem. Each node represents a request for a session and doesn't contain any data on a specific process. A process doesn't need to know which process enters before him, only if there is a conflicting process or if the process before him requested the same session and is enabled, which means it can enter the critical section. A process may enter its critical section if either it's the first in the queue, or the process before him requests the same session as him and is enabled, or the node before him is inactive, which means all the processes before him already exited the critical section, then the critical section is empty, or the last condition is if its own go flag is true. This flag is initialized with false and can become true by the process before him, the successor, if they request the same sessions, then the successor wants to help him. Otherwise, if the successor requests a different session, then this flag can become true if the head reaches its own node, and then the process in the exit section changes the go to true. Each process that exits the critical section tries to advance the head by exactly one step to the next node. If it succeeds, it changes the go flag of the new head to true. Otherwise, it notifies that another process should advance the head by one step for him. So now that we know the idea for the algorithm, let's look at an example. The algorithm uses two shared pointers, head and tail, that are initialized with null values. Each process has two nodes that are shared memory, and in the DSM we can assume that both nodes are in the process's local memory. A process uses a single node in each iteration, meaning one entry, one critical section, and one exit, and in the next iteration the process switches to the other node. Each node contains 5 fields. Session represents the session this process wants to attend. Go indicates if the process may enter its critical section or it must wait on it by local spinning. Active indicates if the node which represents a process's request is still active or may be released. Status indicates if the process is enabled to enter the critical section. And next, a pointer to the next node in the queue. So assume A has already entered the queue, then head and tail point to A's node, and A's spread is null because A is the first in the queue and no process entered before him. But before A changes its status to enabled, B wants to enter the queue. In a fetch and set operation, tail atomically points to B's node and returns A's node, tail's previous value, to B's node. In a second operation, B notifies A that it is after him by setting A's next to point to B's node. Now B checks its predecessor, which is A, and sees that its predecessor requests the same session as him, but is not enabled. So B waits on its go until its predecessor will notify him that they can enter the critical sections. Next, A changes its status to enable and checks if its successor, which is B, needs help to become enabled. In this case, A helps B to become enabled by changing B's go to true. Now C wants to enter the queue and request the same session as A and B. Using a compare and swap operation, C sees that its predecessor, which is V, is enabled and lets its predecessor know that C doesn't need help to become enabled by setting no help value in its predecessor status. Next, C marks its own status with enable value. These three processes, A, B, and C, enter their critical sections concurrently because all of them request the same session X. Now another process D that requests a different session Y that is different than X wants to enter its critical section. D adds its node to the queue and sees its predecessor node is still active. So it asks for help once this request won't be active anymore, and D waits on its go. B completes its critical section and using a mutual exclusion lock, advances ahead by one step. This mutual exclusion lock must have several properties, so this algorithm will satisfy all the properties mentioned before. You may see all these required properties and examples for such mutual exclusion algorithm in our paper. After B advances ahead by one step, it changes the goal of the new head to be true. Notice that B doesn't necessarily advance ahead from its own node, but just advances ahead by one step. Next, C completes its critical section, and again, using the mutual exclusion lock, C advances ahead by one step and changes the new head's goal to true. Finally, A, the last process from session X that is still in the critical section, completes its critical section and also advances ahead by one step. Now the new head is this node, so once A changes the new head's goal to true, D becomes enabled. To conclude, our algorithm satisfies these properties, and by weakening the concurrent entering and the bounded exit properties, our algorithm overcomes the lower bound of Danneken and Zilakos and is the first to achieve a constant RMR complexity in both the CC and the DSM models. Also, is the first to work with arbitrarily many processes and sessions. There are still few open questions such as, is it possible to write a group mutual exclusion algorithm with constant RMR complexity by weakening only the concurrent entering property and leaving the bounded exit as is? It is possible to prove using Danneken and Zilakos lower bound proof with minor modification that the lower bound holds also when replacing only bounded exit with group bounded exit. So it's necessary to replace concurrent entering with a weakened version such as group concurrent entering. However, it's an open question whether we need to weaken the bounded exit property or may leave it as is. Other two interesting problems are to create abortable and recoverable group mutual exclusion algorithms based on our algorithm that satisfy all the properties that our algorithm satisfies. Thank you for listening.